All right, I hope everyone is doing well. Today I wanted to talk about in this YouTube video about t-test. It's something that confuses students in terms of the differences between a one sample t-test, paired sample t-test, and an independent sample t-test. What are the differences between these t-tests, and how do you calculate these t observed value? Well, I'll mention the about observed t-value, how it's calculated, but usually we have statistical software like SPSS and JASP that allows us to calculate a, a t observed value and then the p-value. And so the formulas students usually don't learn about except in the second year course or a third year course. And after that, well, they forget about it. And most of us do forget those formulas, but it's helpful to understand the mechanics of the t-test. Why is a t-test present and how the calculations are done? Um, a good way to learn about the use of such tests is to apply it to use examples. And one example I can use in terms of an experiment, we can also use t-test in survey analysis, but let's think about an experiment. So here in this famous landmark study by Elizabeth Loftus in 1974, Elizabeth Loftus and Dr. John Palmer asked people to watch a video of a minor car accident. So it was just an act. So this is the actual car accident over here. A blue car hits a red car, but it was a minor car accident. It wasn't that um, effect. Like you don't see a lot of broken glass. It was like fender bender. And what was interesting is when the experimenter asked the students, participants, after watching the video clips of this actual accidents, um, how they changed the wording of the verb. So it was either hit or it was smashed and or contacted. So hit would probably be the control condition, smashed would be a in terms of a more the change in the verb. So it would be the experimental condition. So I believe there were two groups. I'm not sure if it was independent design or paired design. So independent design, you would have two groups. One group would hear the hit in terms of the wording of the question versus another group would hear the smashed. Or you would have it, all participants undergo both conditions where you have the car, they hear the question with the hit in it and the question with the smash in it, and hear the question with the contact in it, right? And they're supposed to report the speed and the broken glass. But what you can see from this figure, so this is an actual car. So it is a question of ecological or external validity if this experiment would have applied to eyewitness, people who had actually experienced in a car accident. So here you have how fast were the cars going when they smashed into each other, how fast were the cars when they go contact each other. And you can see though when the wording was changed from contact to smashed, a higher speed estimate was reported. So 40, I guess that would be like a 80 kilometers per hour. Whereas here, like they're reporting 30 kilometers miles per hour for contacted. So the wording of the verb in this case, which is the independent variable, affected the speed estimate, which is the dependent variable. And so this was a landmark study because it led to other research by Elizabeth Loftus. She looked at people who had were innocent but had been un incorrectly put in jail. And that's applicable to justice system, forensic psychology in terms of, um, and it was important because now you can see how police officers or lawyers, how they would question an eyewitness or a eyewitness who had viewed a robbery or someone who had been um, assaulted by an individual, right? And now they're saying that individual is the person who assaulted them, right? Now, if the questions of how the question is worded affects the person's memory, then that suggests that people are reconstructing their memory of the event. And Elizabeth Loftus showed that our memory is Many people believe that memory works like a recording device. Memory works a bit more like a Wikipedia page. You can go there and change it, but so can other people. And that's interesting, right? And she pointed out the idea of intrusions and misinformation, which is often now present in the world today with social media, where you have information that is false, but it affects people's views. So this is highly prevalent in the justice system. We do see innocent people unjustified put in incorrectly in jail when they haven't committed the crime. And it's a lot to do with misinformation, how the witnesses are questioned in the jury and so forth. So that's about that. So the factors influencing misinformation effect, discussing the event with other witnesses, news reports, repeated exposure to misinformation, times, how long it took. The misinformation effect refers to the tendency for post-event information to interfere with the memory of the original event. Researchers have shown that introduction or even relative subtle information following an event can have a dramatic effect on how people remember. All right, so let's go to t-test. So now imagine you are the experimenter and you want to examine the misinformation effect and replicate Lotha's study. So you take a sample from a population, 10 participants from maybe 60, I guess, maybe a population of 1,000 people. And what you find is population of 1,000 people, when they hear the word smashed, they report uh, the verb smashed. They report 90 kilometers per hour on average, right? Now, what about from your sample and you apply this question, you word the verb in terms of smashed, and you find that they report 65, 80, 75, 80, and you get a mean average of 78, right? Now, how do you test the difference if 90 is significantly higher than 78, right? And initially you have to have an hypothesis. Your hypothesis will likely be probably maybe you could say that it could be a directional, that there are individual differences between people that influences how they recollect the event itself. And so that affects their speed estimate. And some people, and it has been shown there are individual differences in how people are misinformed. Some people are easier to be misinformed, where others are less misinformed. So it is possible that a sample of only 10 people may be less misinformed by the word smash, right? So you can have two types of hypotheses, and two-tailed and directional. So directional is if you predict lower, in this case, null hypotheses would be that it's greater in terms of you're from the sample or similar to the 90 kilometers per hour. So that's the null hypothesis. And your alternative hypothesis would be that the mean from the sample is less than the population estimate of the kilometers per hour. Now, in terms of a two-tailed test, well, here you would predict that the means would be the same in the sample and in the population would be the similar, right? So the mean of the sample, which is this symbol over here, is the same as the population. And you would then have an alternative hypothesis where the mean is different from the mean of the sample is different from the uh, population sample. So you haven't indicated if the sample mean is lower or higher in terms of the two-tailed test, but in terms of the directional, you do predict the direction. And usually you get a more significant effect with the directional than two-tailed test because I guess, and you would say that two-tailed has more power, but most researchers prefer to go with the directional in order to get more significant effects. But that's another story. So you get the mean 78 and standard deviation 6.32. But something about t-test here. So imagine you're looking at average height. Here's your average height, and you find the average height from your sample is 5, and so it's above the mean, but how far is it from the mean? And so you use this t-distribution, which is similar to the Gaussian normal distribution of the z-score, where the mean falls in the average. And then if your score is significantly in standard deviations further away from that mean, based on a t-critical value, then you can say that it is significant, right? So the probability is the value area under the curve. So here we have a t-test of one sample, and you can have a critical value here, 2.26, 2.26 negative. So it can be in one direction. So if it's greater than, I guess it would be t plus 2.62. So let's say that's 5. Or if your sample has a height of 2, which is quite low, then and your probability would be, let's say, 0.05, and you choose that, and your t-value is greater, calculated t-value is greater than this, then you can say you can reject the alternative, the null hypotheses and accept the alternative hypotheses. Right. So we have the mean here. We have a standard deviation, and we know there are 10 participants here. Our standard error of the mean, how that is calculated is by taking the standard deviation divided by the square root of n, which is the number of participants, which is 10. And so you get 2.0. And then you get the degrees of freedom, and this is how your variability, and it relates to variability in terms of the degrees of freedom, but you want to make sure your mean is not part of the variability, because that would reduce the variability. So you want to keep that in mind, and then the hypothesized mean is 90, so this is the population mean, and the t observed is what is calculated. So how you calculate the t observed is subtracting the mean, which we had as 78, with minus the 90, which was the hypothesized mean, divided by the standard error, which is 2.0, which was calculated here. And you had the standard deviation divided by the square root of the sample size, and then you get negative 6.00, right? So that's the t observed, the one which was calculated for the one sample t-test. Now to look in the t-distribution table, we have to look for n 10, and our p-value we are setting as threshold 0.05. 9df is the degrees of freedom, and then actually, sorry, this should be one sample t-test. One sample t-test, and we have it at -6, and then the t-critical, and so this is the from taken from the table. So here I'll show you our value here. So we have 10, right? 10, and then we have, what is it? 10 and 0.05 is p, and then 90 at 10, 0.05, and 10, 0.05, right? So let's say we take a directional of one tail, and then we also have two tails is here 0.05, but one tail is 0.05, and we have 9, so it's 1.833, right? So that's our one sample t-test right there. Degrees of freedom, and we have our p-value is 0.05, 9 df, and so our t-critical, so if our t observed is higher or lower than this, I mean higher than this value, that means that it's significant. Yeah. But we do expect a negative value because it's lower, right? But how lower is it? Very long terms. And it's a negative 6.00. And so that suggests that it is a significant effect. T observed for -6. And if you look at that table again for the two-tailed test, so let's do the two-tailed test, which is df9, p is equal to 0.05, and then we have n is equal to 10. Where did I put that? Hmm. All right, so I'll bring that later, but in terms of the distribution table, let's see. And you can get that value from there. Um, start. Let me, so that's how it explains in terms of the negative 6.00 and then how far it is. And we get these two values from the t distribution table. So here's the t distribution table again, and I can show you at p is equal to 0.05 when it's here, right? There you see it. And we can see, so this is t for the two-tailed test, and it is p is equal to 0.05, the DEF is 9, and we get 2.262. So it's not 2.263. So that should be 2.62. And so that means that our -6 is actually, so you can see it's plus or minus here. So it's further away from this, so it must be significant. If t observed is greater than t critical, then significant. It's much less also than t critical here. It's a negative value, then it's significant, right? Now, let's go to independent sample t-test. So this is the case where you have two different samples, right? You have two different groups. And so let's say we test one group with the word contacted, and we test another group with the word smashed. And so these are the values that are obtained. So you have 90, 80 speed estimate. So the participants who heard the word smashed, on average, they reported an 18 miles per, so this would be the mean, 81 miles, 81 kilometers per hour. So let's keep that in terms of the Canadian system, I guess it's different from the metric American system. And here for the contacted, it's a much lower speed estimate. It's 55, right? 55 kilometers per hour. Now, so what would be, so why is this independent groups? Because one group of participants, 10 participants are exposed to the word smashed, the verb smashed in the question, whereas another group is exposed to the verb contacted in the question. So now you have, is 81 bigger than 55? That is the question. But before the experimenter did this experiment, they had to have a hypothesis, and they had two hypotheses. One, there would be no difference in speed estimate between the smashed and the contacted groups. And their second hypothesis would be that there is a difference in mean speed estimate. So that would be not a directional hypothesis, but more of a, what did I refer to it? So this is a two-tailed type of test. So there would be a significant effect, but the direction of the effect is not mentioned. But if you said, for example, H alternative is equal to, the alternative hypothesis was equal to mean 1 for smashed greater than mean 1 for contacted, then that would be more of a, I believe, more of a significant, of a directional hypothesis, right? More of a directional hypothesis. So this one would be more of a directional hypothesis. Now, so how do we do the analysis for an independent sample t-test? So you have to get the means, obviously, and you have to get the standard deviation. And so we have, in each group, we have 10 participants, right? Now, so you get the standard deviation for one group, and then you get the standard deviation for the other group over here. So we have 26 here. I mean, 5.26, 2055, and then we have 81, 6.99, and then 5.27. So this is standard deviation on the mean. Obviously, 81 is bigger than 55, but is that significant? So it seems that participants who were in the smashed group were more likely to report higher speed estimate than those who were in the contacted group. Now you can do a pooled standard deviation. You have to calculate that, obviously, but usually if you have software, you can easily calculate that value. So the pooled standard deviation is calculated by SP square root of SP squared. But first, in order to get that value, we need to get the two standard deviations for each of the groups and get the variance, so square the standard deviations. And then we add the two variances together and divide by 2. So that will get our pool variance. And our pool variance, to get the standard deviation, we just take the square root of the pool variance, right? So that value there. So let me zoom in a bit more for you. I think zoom. Yeah, so let me zoom here. So now you can see what I mean. So you get the variance, and then you have the variance for the contacted. You just square the square the standard deviation for the smashed, and square the variance for contacted to get that variance, and then you add the two variances together and divide by 2 to get the pool variance. So we get 38.33. And then the pool standard deviation is just the square root of the pooled variance, right? Now, so you get those values over here, and you get your DF. So interestingly, your DF, you have to add the two samples, so 10 plus 10 minus 2 to get your degree of freedom. And so that's 18. And then let's keep our threshold at P. So let's assume this is a directional hypothesis, right? Now, what is going to be our T observed? To calculate that, we have to take the mean over here for X1 for the first group and then the second group. And then our pooled calculation here, which we did calculate over here, which was 6.19. Then you would multiply it by the square root of 1 over 10 plus 1 over 10, right? And that will give you your T observed. And our T observed for the independent sample t-test is 9.39. Now, in order to look this up in the T distribution table, let's go ahead and look at it in terms of the one-tailed and the two-tailed test. So one-tailed, we have here let's assume is 0.05, right? And you have a degrees of freedom of 18, and it is 0.05. So it should be 1.734. So this should be 1.734. 1.734. And if I look at the degrees of freedom, which is 18, right? 10. Oh, actually, wait. You have two groups. Yeah, 20. Yes, 20 minus 2 is 18. That's correct. So that would be 1.734. And then if you have one-tailed, so we did one-tailed, and your degrees of freedom is 18. So let's see. One-tailed degrees of freedom is 18. So here's one-tailed over here in 0.05, and it's 1.734. That's correct. Now two-tailed 0.05 here, and our two-tailed is degrees of freedom is 18, and so it's 2.101. So 2.101. And our calculated T observed is 9.39. So this was the calculated. So if you use this equation, you would get the T observed. And it is greater than the T critical, so that's significant, and that's significant for both one-tailed and two-tailed test. And we can reject the alternative hypotheses in either case, or if it's uh, there is a difference in speed as mean speed estimates for the between the two groups. And we can also say, in terms of the directional hypotheses, that there's higher speed estimate for the smashed compared to the contacted group. And here's a p-value which is calculated. I simply used the Excel formula for the t-test, and I found this value. So you can actually just input your values in a proper format, and then use Excel to calculate the p-value. But Excel won't give you the t critical value, right? I think software like R and JASP and SPSS can give you the t critical value, right? Now, if you think about the t-test distributions, this is what I found from a website, helpful website. So you can have two different distributions. But if the two distributions are overlapping, right? So this is the pool t value over here, then that means the means are the same. But if they're not overlapping, so in this case, maybe the t value for both distributions is different, right? Maybe it's somewhere here, or it's not in this probability value over here. That will mean that there's certainly a difference between the two t distributions of the two groups. Now let's go to paired sample t-test. And here you have a two related sample over here. And basically, you have uh, the one sample over here, one t distribution. Now, how would you do this now? So how is this different from where you have the case of an independent sample t-test? Well, in the case of a paired sample t-test, you have two groups, right? You have the participant going through both the conditions, the smashed and the contacted. And so they hear the word smashed as in the question, and they report a higher speed than the contacted. And you can see that in the example here. So all participants hear the question with smashed, and all participants also hear the question with the contacted. Whereas in the independent sample one, you have one group hears the word smashed versus another group hears the word contacted, right? Now you need to get the mean. Obviously, we can see 81 is bigger than 55, but that doesn't support, it could still be non-significant because of the high error or individual differences. So what are your hypotheses? Well, your hypotheses are the mean difference would be equal to 0. So that if you subtract 90 minus 80, for example, and get 10, or 90 minus 90, and that means it's 0. There's no difference between the two groups. Not much of a difference is 90 or 80, right? But if there is a big high mean difference, then there is a difference, right? And so this hypothesis is there's no difference in mean estimated between the two wordings. And you could, that would be the first hypothesis. Or you could have more U difference or equal to 0, smashed is not higher than contacted. So that would be a directional hypothesis for your null hypothesis. Then there is a difference. So here it's not directional in mean between smashed and contacted. It's not indicated if the mean estimate would be higher for smashed or would be higher for contacted, right? Now, if you do one-tailed alternative hypotheses, here we have the difference. So this is actually a two-tailed test. U difference, so I would say it would be H is the mean difference is greater than 0. That would be more about this would indicate that smashed yields higher speed estimates than the word contacted, right? Now, how do we calculate the t value here? Well, the difference from the independent sample t-test is here you have all the participants are exposed to both levels of the independent variable, contacted or smashed, right? And so you have the mean difference first, and you get the square of the mean difference. And so here's the manual calculation of that, 196, and then you add them up together, you get 790. Now, so that's 790 here, you get the sum of it, and then you divide 790, the square root of 790, divide by 9, which is the degree, and gather 790 divide by 9 because it's n minus 1, and then you get 9.37, which is the standard deviation for the two standard deviation of the mean difference, which is 9.37, right? N minus 1 is underneath here, so it's 790 over n minus 1. And the mean difference is 26, right? And we get the mean difference here because we get the average of here, average of the mean difference, and the standard error of the mean difference is simply standard deviation by the square root of n. We have our degrees of freedom, which is n minus 1. And then we get the p-value we set as our threshold, and right now we are having a directional hypothesis. So our calculated t observed value is 8.78, calculated from this t value. T is equal to the mean difference in this case, so the mean difference, and divided by s over n, right? So UD 26 over the s standard deviation divided by the root of n, right? SD 9.37. And what we get is this t observed 8.78. So now we have to look in the distribution table. So if you look at here, so we said 8.78, and our t critical for a paired sample t-test with a degree of freedom of 9, so 9, and it's 1.833, right? You see that, 1.833. So we have 1.833 degrees of freedom is 9 at a 0.005. So this would be for the one-tailed test, one-tailed. And for the two-tailed, well, we have it at 0.05. That's at 9, that's 2.262, right? So that now our t value is found to be 8.78, but that's much bigger than our t observed, our t critical. And this is our t observed. So that means that when we look at our distribution, our t observed is over here, and our t critical is over here. And I guess this would be how it would be. But you can see then that means that our t observed is greater than our t critical, so it's significant. And we had a threshold of p is equal to 0.05. Now, if we wanted to, I guess, look at how we calculated the p-value is here. You can calculate in Excel, but I just wanted to show you how it is done in Excel in terms of the calculation. So that explains the mean difference, and then we get the divided by the standard deviation, 9.3 over 37 over the root of n, and you get the t value, right? And you compare it. So it seems that we can reject the null hypotheses, reject the null hypotheses and accept the alternative hypotheses, whether it be for directional or non-directional. All right, so I hope that it helps you in terms of understanding a t-test in terms of independent sample t-test and a paired sample t-test and a one sample t-test. Thank you.